Have you ever looked up at the night sky and wondered, where did all of this come from? It's a question that has captivated humanity for millennia. Today, we're re-diving deep into the very beginning of everything, the Big Bang, and exploring an inconvenient element that cosmologists are still struggling to explain. Think of our universe as a giant, cosmic jigsaw puzzle. Scientists, the brilliant puzzle solvers of our time, have pieced together an incredible picture. They've told us that about 13.8 billion years ago, our entire universe was compressed into a point of unimaginable density and heat. Then, in an instant, it began to expand. This is the Big Bang theory, the cornerstone of modern cosmology. Now, imagine trying to solve a puzzle, but the most crucial, central piece is missing. Or maybe it's just blurry and we can't make out the image. That's the challenge cosmologists face when they try to peer into the first moments of the universe. We're talking about a time so early. It's a fraction of a second after the Big Bang. The conditions were so extreme, so alien, that our current laws of physics begin to break down. In this primordial furnace, the temperature was trillions upon trillions of degrees. It was so hot that the fundamental building blocks of matter, protons, neutrons, and electrons, couldn't even exist. The universe was a sizzling, chaotic soup of energy and elementary particles, expanding at a mind-boggling rate. It's a state so far removed from our everyday experience that it's almost impossible to visualize. So, how can we be so sure about any of this? How do we know what this ancient universe looked like? Well, the universe left behind a clue, a faint, ghostly afterglow from its fiery birth. It's called the cosmic microwave background radiation, or CMB. Imagine you're standing in a room where a massive firework just went off. Even after the flash is gone, you can still feel the warmth lingering in the air. The CMB is that lingering warmth, a faint microwave light that fills the entire cosmos. Discovered in the 1960s, this radiation is a near-perfect snapshot of the universe when it was just 380,000 years old. Before this time, the universe was an opaque fog, but as it expanded and cooled, atoms could finally form, and light was set free to travel across space for the first time. The CMB is that very first light, stretched out over billions of years into microwaves by the expansion of the universe itself. When we map this radiation across the sky, we see a stunningly detailed picture. It's not perfectly uniform. There are tiny, almost imperceptible variations in temperature. These minuscule fluctuations are incredibly important. They are the seeds from which all cosmic structures grew. The slightly denser, cooler spots were the gravitational anchors that pulled in matter over billions of years to form the first stars, galaxies, and the vast cosmic web we see today. We are, in a very real sense, looking at the blueprint of our universe. But here's where the puzzle gets tricky again. While the Big Bang and the CMB provide a powerful framework, they also present us with profound mysteries. The standard model of the Big Bang, for all its success, can't fully explain why the universe is so incredibly uniform on the largest scales. Why is the temperature of the CMB almost exactly the same no matter which direction we look? To solve this, scientists proposed an idea called cosmic inflation. This theory suggests that in the first sliver of a second, the universe underwent a period of hyper-accelerated expansion, growing exponentially in an instant. This would have smoothed out any initial irregularities, like stretching a wrinkled piece of fabric until it's perfectly flat. Inflation elegantly solves the uniformity problem and also explains the origin of those tiny fluctuations in the CMB. But here's the inconvenient part. We don't have direct proof that inflation actually happened. It's a brilliant, mathematically sound theory that fits the data beautifully, but it's still a theory. It's like having a suspect in a mystery who has a perfect alibi and motive, but no smoking gun. Scientists are searching for specific signatures in the cosmic microwave background, a type of polarization pattern that would be the definitive evidence for inflation. But so far, the search has been elusive. And that's not the only unexplained element. Our best theories predict that the Big Bang should have created equal amounts of matter and its counterpart, antimatter. When matter and antimatter meet, they annihilate each other in a flash of energy. So, if they were created in equal measure, the early universe should have been a cosmic battleground that ended in a stalemate, leaving behind nothing but a sea of radiation. Yet, here we are. The planets, the stars, the galaxies, you and me, were all made of matter. For some reason, a tiny fraction of matter survived this cosmic annihilation. For every billion antimatter particles, there were 1,000,000,001 matter particles. That one is everything we see. Why this imbalance? We simply don't know. It's one of the biggest, most fundamental unanswered questions in all of science. It's an inconvenient truth that points to new physics, to something beyond our current understanding. So, while we've assembled much of the cosmic puzzle, some of the most critical pieces remain missing or unexplained. We have the lingering echo of the Big Bang in the CMB, but we lack the definitive proof for the inflation that might have kicked it all off. We have a universe full of matter, but no solid explanation for why it exists at all. This is what makes cosmology so thrilling. It's a field on the frontier of human knowledge, constantly pushing the boundaries of what we know. Each discovery, like the CMB, answers some questions but often opens up a whole new set of deeper, more perplexing ones. The universe isn't just giving up its secrets easily. It challenges us, teases us, and forces us to be more creative and more brilliant. The quest to understand our origins is a fundamental part of the human spirit. We will continue to build better telescopes, devise cleverer experiments, and dream up bolder theories to fit the pieces together. The inconvenient elements aren't failures of the theory. They are signposts, pointing the way toward a deeper, more complete picture of our cosmic home. Thank you so much for joining me on this journey to the edge of time and space. If you enjoyed this cosmic exploration and want to learn more about the mysteries of our universe, make sure to hit that like button and subscribe to the channel. Let me know in the comments what you think is the biggest mystery of the cosmos. Thanks for watching, and as always, keep looking up.